Hi, everybody. I hope you're doing great. I hope that the school thing is working for you. So weird. We only have, after this week, you'll have 2 weeks left of physics. If you're a senior, you'll have 1 week left. And I hope you're enjoying the beautiful, warm summer weather we have outside. So, we've had a lecture on the theory, no, on Einstein's equivalency formula, E equals mc squared. And I explained that actually doesn't have very much or anything to do with the theory of relativity. It was written and um, published in a separate paper in 1905, and it just helps us understand how much energy is created in any reaction, any energy transformation. It could be nuclear, it could be chemical, but it allows us to understand that mass and energy are equivalent. They're two sides of the same coin. Sometimes mass is converted and turned into pure energy. We can calculate just how much that is. In fact, whenever energy is created, mass is destroyed, and vice versa. So, fascinating, but different from the theory of relativity, which is what our topic is today. I'm hoping today I can give you a very simple definition of what the theory of relativity means and introduce to you a little bit of how, while that's easy to understand, it has some implications for our reality in the universe. And those consequences of the theory of relativity are really unfamiliar to us, so they sound crazy. And that's where the fun starts. Now, before we get into that, I want to just review physics. What is physics? Well, it's just our best job of trying to understand the world around us from some common experiments that could be repeated. And as more and more people do this, we get better at it. Now, of course, as more and more people do this, we get a little more specialized and we get more specific, precise questions. And we start describing more extreme situations in the universe. And all of a sudden, we are in a realm that has less to do with our experience, and therefore it doesn't make as much sense to us. Still, it's all about the reality of the world around us. What needs to expand is our acceptance of that reality. So our common sense is going to be working against us. Now, Einstein did most of his work as thought experiments. He called them Gedankens. And one of his first ones, I think Nick will like this, he came up with at age 16 while riding a motorcycle. He imagined someone throwing a baseball really fast, let's say 100 miles an hour, although he was in Europe and dealing with the metric systems at the time. But imagine he could go accelerate on his motorcycle, vroom, up to 100 miles an hour and pull up alongside that baseball and look over at it. He'd see a little baseball floating in the air, right? Going the same speed as him. You could just look at it. You could see if it was spinning or not. Similarly, if there was a bullet shot out of a rifle at, let's say, 1,700 miles an hour, and his motorcycle could go 1,700 miles an hour or faster, he could pull up alongside that bullet, and they'd both be going zoom at the same speed. Him on one side, the bullet on the other. He could look over at it and see that bullet. Seemingly, it would look like it's just floating in the air there, and the world was whizzing past them both. And he could see whether or not the bullet was spiraling, right, or not. So he asked this question: what would I see if I pulled up alongside a light beam? If my motorcycle could go the speed of light, and I were to pull up alongside a light beam and look over at it, what would I see? Cool question. So we'll answer that today. But first, let me give you the basic definition for the theory of relativity. It states simply that the laws of physics are the same everywhere. That's it. Theory of relativity is the laws of physics are the same for all reference frames in continuous motion. Now, the general theory of relativity, or the theory of general relativity, got rid of that continuous motion thing and expanded this quite a bit. So the theory of special relativity is specialized because it deals with a more constrained, narrow part of the universe or set of reality. And it is specifically things moving in a straight line without speeding up or slowing down or turning, in continuous motion in an inertial frame. And then a different circumstance with a different type of motion, as long as it's in a straight line, it's not speeding up or slowing down, a different inertial frame could have a totally different view on reality. And both of them are valid. Both of them are real. There is no one real situation and then the other one's different because it's moving. They both are 100% correct. But the perspective on reality is different. They would experience some things like time differently. So that's basically the definition. And you already understand that. That's pretty simple and should make sense to you. Actually, even just with our limited experience as human beings on this planet Earth, we have enough life experience to appreciate this. So let's consider our own little thought experiment. We're going to do some experiments here. Imagine that you're playing catch, but now you're on an airplane. You're moving at 300 miles an hour. Could you go into the aisle with a friend and toss a ball back and forth? Of course. Would you have to take into account your distance, your exact distance between you and the center of the Earth's mass? No. Would you have to take into account your velocity relative to the center of the Earth? Would you need a calculator? Would you need to do any calculations at all? No, you just play catch. Okay, similarly, you go to the bathroom on that airplane and you see a microwave there and you warm up your cup of coffee. You stick it in there and press the button for 1 minute to warm it up. Would the microwave work? Would you have to take into account your distance from the center of the Earth or your velocity? Would you need to do any calculations at all? No, you just hit the button and turn on the microwave. Okay, so the basic analogy here is this. The ball of catch represents gravity and motion, velocity, acceleration, the kind of things we're talking about in basic classical Newtonian physics. The microwave represents the laws that deal with electromagnetism and the speed of light. And yet they both seem to work. It doesn't matter that we're moving at 300 miles an hour on an airplane. The laws of physics still work. How about if we're living on another planet? Now we're somewhere else in the solar system. Could you play catch? Could you warm up your coffee in a microwave? Would you need to do any calculations at all? No. The laws of physics still work. And this would be true even in the extreme circumstance of us being in another galaxy. Far away, let's say, moving away from Earth as the universe expands, 80% the speed of light. Could we play catch there? I mean, maybe gravity is different and stuff, but we'd be stronger if we used stronger gravity. Maybe we need more force to fight the gravity, but you could play catch there, right? We need to have a generator to create electricity, but if we did, we could plug in our microwave and it would heat up stuff, right? And we wouldn't need a calculator. We wouldn't need to do any calculations at all. The laws of physics are just the laws of physics. They work fine in other situations, in other places. All right, so this guy Aristotle would have answered that differently. He believed that the Earth was special, divinely created, surrounded by an ether. I don't know exactly what that was, but he had it floating around it, suspended in this ether. And then there were these crystalline spheres that were perfectly spherical. And in them, things like the planets and the stars moved in with divine motion and a different set of physics, a different set of laws for those motions. So you're doing better than Aristotle already, and you understand the basic concept of relativity. That being that the laws of physics are the same everywhere. Ooh. And I'm having technical difficulties already. Okay, going the wrong direction. There. This was Einstein's insight. Now, it does get complicated, but it isn't the definition of relativity that's complicated. He said, the laws are the laws. Physics works the same. That's basically how the universe works. So it works anywhere in the universe. Any reference frame is as good a place to do physics experiments as another. And we can expect the laws of physics, including, for example, the speed of light, to be the same in all reference frames in all parts of the universe. Now, there we go. He had this cute quote. He had a lot of brilliant and kind of timeless quotes on a variety of subjects, but here's being a little bit playful. And you can appreciate that. Sometimes you're in a really boring lecture and maybe it's your science class. You sit there and just, time drags on. Will we ever get out of here and get to go to lunch? And sometimes you're really enjoying something. You're like, oh man, is it time to go already? Right? Things are kind of relative. And in fact, not only did Einstein say that everything other than the laws of physics are relative depending on your motion, your situation, but specifically time is one of those things that is different in different realities. Now, a hero of his, and I think a contributor to all of his work, James Clerk Maxwell, preceded Einstein a little bit and came up with these brilliant insights, Maxwell's four equations that all dealt with light, electromagnetism. In fact, he's the one who first calculated that the speed of light must be about a little less than 300 million meters per second. Einstein realized, wow, that's going to do some pretty weird things. Including, it's going to mean that it doesn't matter if the light source is moving towards you or away from you. You'd always measure exactly 300 meters per, a little less than 300 meters per second as a velocity, which is pretty weird. And most people said, well, that's just wrong. Einstein said, no, I think it's right. Here's what that would mean. Basically, let's say you're on a sidewalk and you see a street light and you have your little fancy dancy light measurer and you measure the light whizzing out at you from the street light and you'd clock it at the speed of light, c, a little less than 300 meters per second. Well, imagine now there's a rocket ship flying past. It could go either way. Let's say it's going towards the lamp and you, and it is traveling at 50% the speed of light. And they had on board a little fancy light measurer, and they measured the speed of light coming out of that lamp. Even though they're going half the speed of light themselves, right towards the light coming at them would go into the little measuring device, and they would clock it at exactly c, the speed of light. And it wouldn't matter if they were actually going away from the light source at 50% the speed of light. Now the light has to work extra hard to catch up to them. They would still measure exactly the speed of light in that situation. Everybody, doesn't matter what your situation is. If you're going 99% the speed of light and you're going away from it, light has to work really hard to catch up to you. You'd still measure it hitting you at exactly the speed of light. In all situations, in all reference frames, every measurement of the speed of light is exactly the same. C, the speed of light, 300 meters per second. So that's when people started saying, okay, well, that can't be wrong. Maxwell Clerk's just incorrect. And Einstein disagreed. Einstein said, no, this is just reality, and it's foreign to us. So, common sense is based on what's familiar to us, and physics is based on common sense. Which is why most kids teach themselves to walk and crawl. The reaction when you throw your spoon on the floor as your little toddler strapped into your chair at age 1, it's kind of the same every time it falls and hits the floor and the food splatters. Gravity is gravity and it just works the same. And now we talk about this going 50% of the speed of light, and lots of things seem unfamiliar to us. It's basically the case that moving forward from here, our common sense is going to work against us because our life experience is so limited when compared to these extreme situations that Einstein envisioned. So we have no experience moving close to the speed of light. It'd be a different situation. You wouldn't need this lecture if you were used to crawling around and falling off your chair as a toddler and you're learning to ride a bike and you're doing all that stuff at 10% of the speed of light or 30% of the speed of light, 30% c, right? You wouldn't need me to explain anything. It'd just be familiar to you. For now, then, what you need to do is try and suspend your disbelief, try and expand your common sense to consider the stuff I'm talking about. Okay, so here's our definition. If the laws of physics are the same everywhere, and yet we end up with some of these weird situations, some of the things we assume should be the same everywhere, they've been the same everywhere in my life experience. Some of those things aren't absolute at all, but actually change from one situation to the next. So there's all sorts of things that aren't the laws of physics that are relative. Yeah, it just depends. And time is among them. So we assume that we all know what time is. Not seconds and hours and days. That stuff is we made up, right? We call seconds something else in different languages, right? A day is pretty random because if you don't live on Earth, the time it takes for our planet to rotate once on its axis in the light of our nearest star, well, that doesn't mean anything to you, right? A year is how long it takes for us to orbit around that star once. Well, that doesn't mean anything to you if you're living on Venus or in the Andromeda galaxy, right? But more than that, how fast our cells age or iron rusts, how fast a quartz chip will vibrate and oscillate in an electrical field, or how quickly a cesium atom decays. Just our time itself is different in different places. Time is relative, and lots of things. Space is relative. So, both of the videos I showed you that talked about Einstein's light box, the concept is a convenient way to kind of approach this. Now, the clock here is a bit of light moving up and down. It leaves a light source at the bottom and reflects off a mirror at the top and bounces back down. Now, it's doing this at the speed of light really fast. The concept is not that there's something weird about this clock in different situations, the clock that's at rest and the clock that's in motion, but that they experience time differently. Time itself is different depending on if you're at rest or if you're in motion. But because this is a visual clock and it deals with the speed of light, it's a helpful analogy for trying to understand this concept. Light, the speed of light is absolute, it doesn't change. So other things like how far space is, meaning how tall I am, right? How big the Earth is, right? Space itself can change. It's not absolute. And in fact, we think it does change. Time is not absolute. So in this little analogy, just to review what was said before in those two videos, if we have two clocks and compare them, they're both synchronized so that the light source leaves the bottom, let's see here, leaves the bottom, goes to the top, bottom, top, in perfect sync. And we separate them. One is going to remain here with us. One of them is going to be on a rocket ship and moving really quickly past us. Well, the deal is, from our perspective, the single clock that's in our same frame of reference, in our same reality in terms of our motion, we just see it leave the bottom, go to the top, return to the bottom, go to the top, return to the bottom, bounce off the top, back and forth like this. That's all we see, up, down, up, down. But the light clock in the window of the rocket ship that's whizzing past us at, let's say, 80% the speed of light, we'd see the light source there leave the bottom, and then by the time it reaches the top, the rocket ship's in a different place. So as it's going to the top of the clock and the rocket ship is moving laterally, the light source actually moves through space at an angle, reflects off the mirror, and the rocket ship continues to move as the light source goes to the bottom of the clock and goes at another angle. And what we now see is they're still in sync, and they're still both traveling the speed of light. The only speed they can travel is absolute. But the one on the rocket ship is traveling a farther distance as it goes to this weird set of angles. And we think that's true, and we think the explanation for how that could possibly happen is that, first of all, the distance changes. Secondly, time changes. So, time slows down on that rocket ship, allowing, therefore, from our perspective, it would look like their time is going slower, so they would have fewer birthdays, there'd be fewer seconds involved, and there'd be a little bit more time for that light beam to cover that larger distance. Okay, so that is the demonstration that maybe light is an absolute, the speed of light is an absolute number, and things like time are not. Which gets us to this concept of time dilation. We can compare two different reference frames in the universe, experiencing two different types of motion, and they will experience time differently. Both of them will experience time as reality. Both of them will be correct in their understanding, but time will be different in those two different situations. So the twin paradox is basically that we have now two identical twins. So they were born at the same time. One of them becomes an astronaut and takes off in a rocket. Let's say it goes 10% the speed of light, and it does so for 10 light years, and then turns around and returns home. After experiencing that incredible high velocity and being in a very different reference frame, technically two different reference frames, continuous motion going away, and then a turning around moment, which that motion stopped and changed, and then continuous motion coming back to Earth. The brother who was, or the twin who was left on Earth and only experienced one time frame, one reference frame, that person had more birthdays and is older. The entire world is older. And the twin who has traveled, has experienced time at a slower rate, has had fewer birthdays and comes back younger, seemingly has traveled into the future and got to visit his brother, the twin, in his old age. That's the introduction to the twin paradox. It actually is more complicated than that. But it is the introduction to this concept that maybe time travel is possible. Certainly, it's a demonstration, another example of what we think happens with time dilation. In fact, this is one that happens with the atomic clocks on our satellites as they orbit around the Earth. They're moving fast enough, nothing near 10% the speed of light, but 17,000 miles an hour, roughly, on average for all those satellites. Fast enough that those atomic clocks are experiencing time differently. They experience time differently, so they experience radioactive decay at a slower rate. And our engineers need to program them differently. So when they talk to people, to clocks and computers on Earth, the time gets recalibrated to sync up again. Because they're experiencing a different time reality because their motion is so fast. Which is an important thing to know if you're late to class. It's a good excuse for all sorts of situations, late to work, late to court. Maybe that'll help you sometime. So getting back to our definition here, laws of physics are the same everywhere, but all sorts of other things are no longer absolute and in fact change. The first one we're considering is time itself. Getting back to Einstein's thought experiment when he was 16 years old, so what would he see? If he were to have his motorcycle accelerate to the speed of light and you were to look over at a light beam, what would it look like to him? Okay, I'm going to stop here. Our next topic will be simultaneity. The fact that some things are simultaneous, maybe in our reference frame, means that they will have to not be simultaneous in some other frames of reference. My second favorite topic in the theory of relativity, leading way to what we'll talk about next week, which is my favorite topic. So look at those, answer the questions, get back to me, and look forward to this next lecture, which I'll post tomorrow.